I will be presenting about the determination of riboflavin content in a multivitamin. This experiment was performed and the data was collected by me and my partner, Analytical. First, I will talk about the background of this experiment, including the usefulness of riboflavin and the spectroscopy methods used. Next, I will go over how the solutions were prepared for the experiment. Then, I will discuss the absorbance and fluorescence spectra of the standard and unknown riboflavin solutions. Lastly, I will talk about using standard addition to determine riboflavin content in a multivitamin. Riboflavin is also known as vitamin B2. It is found in many foods, including nuts, grains, dairy products, and dark green vegetables. Riboflavin is yellow in color and is water-soluble. It is a component of two coenzymes. These coenzymes are important for metabolic pathways and the usage of carbohydrates, fats, and protein as energy sources. Absorbance and fluorescence spectroscopy are both ways to determine the concentration of solutions based on the detection of absorbance or emission of light. Absorbance spectroscopy shows what colors based on wavelength a solution absorbs from light. The spectrophotometer shines light at the solution, then detects the transmittance. Absorbed light by the solution is the amount that is not transmitted. Fluorescence spectroscopy shows what colors are emitted when a certain wavelength is shined at the solution. When molecules absorb light, the electrons get excited. For fluorescent molecules, as the electrons relax back to their original state, they emit a photon. Non-fluorescent molecules often release energy in the source of heat. So, for fluorescence spectroscopy, a certain wavelength of light is shined at the solution. The spectrophotometer then detects the emitted light by the solution. Absorbance and concentration are linearly related. Solutions of higher concentration have greater absorbance. Fluorescence and concentration are linearly related. Solutions of higher concentration have greater fluorescence. Particularly for this experiment, we are using spectroscopy to determine the percentage of riboflavin in a multivitamin. This multivitamin contains riboflavin and other vitamins and binders. Many of the other components of the multivitamin also absorb light. Thus, the absorbance spectra would not only be that of riboflavin, but also the other vitamins and binders. Fluorescence, on the other hand, is rare in vitamins, so the interferences of other components of the multivitamin tablet in the fluorescence spectra will be greatly less. There are two methods for determining the concentration of riboflavin using spectroscopy. Standard solutions is a method when solutions of different concentrations of the analyte are prepared and the fluorescence spectra taken. Then a linear curve of concentration versus fluorescence can be graphed. Taking the fluorescence spectra of the unknown solution, the unknown concentration can be determined by the linear curve. For standard addition, each glassware is filled with the same amount of the unknown concentration solution. Then, differing amounts of solution with standard concentration are added to each container, and the rest is filled with the solvent. Next, taking the fluorescence spectra, a linear curve of volume of standard solution added, and fluorescence intensity can be graphed. The concentration of the unknown can be found with B, the y-intercept, m, the slope, CS, the standard solution concentration, and Vx, the volume of unknown added. In this experiment, standard addition is a better technique than standard solutions. This is because the multivitamin contains many binders and other vitamins that cause interferences. For standard solutions, the linear curve is made from these pure solutions, while the unknown has interferences that are not taken into account. However, for standard addition, it does take into account of these interferences. Each standard addition solution contains the same amount of the multivitamin solution, which means that each one has around the same amount of interferences. Thus, standard addition is more accurate in determining the amount of riboflavin in a multivitamin. Next, solutions for the experiment were prepared. A 1 liter stock solution of 0.02 molar acetic acid was prepared by adding 5 milliliters of 4 molar acetic acid with nanopure water. This was the standard solvent for the entire experiment. A stock solution of 50 parts per million riboflavin was prepared with 25 milligrams of riboflavin and the 0.02 molar acetic acid stock solution. The solution was heated for the riboflavin to dissolve in the acetic acid. 500 milliliters was prepared in a volumetric flask. This was used for the standard solution of riboflavin with known concentration. For the third solution, 250 milliliters of the unknown multivitamin solution was prepared. 50 milligrams of the crushed multivitamin tablet was added and mixed with a 0.02 molar acetic acid solution. The solution was heated for the riboflavin to dissolve. Next, using the standard 50 parts per million riboflavin solution, 8 standard solutions of varying riboflavin concentrations were made, each in a 25 milliliter volumetric flask. The 8 solutions respectively contained 1 milliliter, 2 milliliters, 3 milliliters, 4 milliliters, 5 milliliters, 6 milliliters, 7 milliliters, and 10 milliliters of the standard 50 parts per million riboflavin solution. Next, the spectra were taken for the unknown multivitamin and standard solutions. Using a SpectroVis Plus spectrophotometer, the absorbance spectrum was taken for the 2 parts per million standard riboflavin solution, the 20 parts per million riboflavin solution, and the unknown multivitamin riboflavin solution. The absorbance spectra was taken for the riboflavin solution to analyze whether the fluorescence spectra should be taken at the excitation wavelength of 405 nanometers or 500 nanometers. As described previously, the electrons first need to be excited in order to fluoresce as they relax. So the electrons must absorb light in order to fluoresce. Therefore, at the excitation wavelength, there must be a significant amount of absorbance. By analyzing the absorbance spectra, the riboflavin solution has the highest absorbance around 434.8 nanometers. The absorbance at 405 nanometers is clearly greater than the absorbance at 500 nanometers, which is almost zero. Therefore, by taking the absorbance spectra, we know that the fluorescence spectra should be taken at 405 nanometers, which has a good amount of absorbance. Next, the fluorescence spectra was taken at the excitation wavelength 405 nanometers for all of the 8 standard solutions that were prepared, plus the unknown solution. Lambda max was chosen to be the wavelength at which the solution of greatest concentration has the greatest fluorescence intensity. In this case, the 20 parts per million solution has the greatest fluorescence intensity at 516.7 nanometers. The calibration curve shows a linear relationship between the concentration of riboflavin and the fluorescence intensity at the excitation wavelength of 405 nanometers and lambda max at 516.7 nanometers. The y-intercept is 0.00 plus or minus 0.01, and the slope is 0.011 plus or minus 0.001 relativity over milliliters. Next, the data was checked to see if there was an inner filter effect. Fluorescence spectroscopy is sensitive and has a limited dynamic linear range. When the concentration of the solution is very high, the light does not pass through the entire solution, so the fluorescence intensity is lower than what it actually is. To check whether there is an inner filter effect, the solution with greatest concentration, the 20 parts per million solution, is taken out of the data from the calibration curve. So this is the calibration curve without the 20 parts per million solution. This new R-squared value is compared to the previous R-squared value. The closer the R-squared value is to 1, the straighter the curve. So if the new R-squared value is closer to 1 than the previous one, then the 20 parts per million solution is likely out of the dynamic linear range. In this experiment, the R-squared value without the 20 parts per million solution, which is 0.9923, is actually farther from 1 than the R-squared value with the 20 parts per million solution, which is 0.9931. So the 20 parts per million solution data is kept inside the calibration curve. Using the standard calibration curve, the concentration of riboflavin in the solution can be determined with this equation. Cx is the concentration of the riboflavin, and Fx is the average fluorescence intensity of the riboflavin solution, B is the intercept, and M is the slope. Using this equation, the unknown riboflavin concentration was calculated to be 13.2 plus or minus 0.9 parts per million. The theoretical riboflavin concentration was calculated using the tablet information. One multivitamin pill was 0.9714 grams, and the riboflavin content in one pill was 50 milligrams. So, the theoretical riboflavin concentration was 10 parts per million. The mass percent of riboflavin in the multivitamin was calculated using this equation, where the mass percent is equal to the concentration of riboflavin divided by the concentration of the multivitamin in the solution, times 100%. The mass percent of riboflavin in the multivitamin was calculated to be 6.6% for the experimental value and 5.1% for the theoretical value. The percent error was calculated using this equation. The percent error is the absolute value of the experimental minus theoretical divided by the theoretical times 100%. The percent error of the mass percent of riboflavin was 28.6%. For the standard addition method, 5 25 milliliter solutions were made. Each contained 5 milliliters of the unknown multivitamin solution and differing amounts of the 50 parts per million standard riboflavin solution. The 5 standard addition solutions respectively contain 0 milliliters, 1 milliliter, 2 milliliters, 3 milliliters, and 4 milliliters of the standard 50 parts per million riboflavin solution. The fluorescence spectra at the excitation wavelength of 405 nanometers was taken for all 5 solutions. By analyzing the curve for the solution with highest concentration, which was the one with 4 milliliters of the standard solution, the emission wavelength was found to be at 515.18 nanometers. So, for the standard addition curve, the fluorescence spectra intensity graphed here was the fluorescence intensity at 515.18 nanometers. As expected, the graph is a linear curve. The R-squared value for the standard addition calibration curve is closer to 1 than that of the standard solutions curve, which matches with the theory that standard addition is a better method than standard solutions for this experiment. The y-intercept with a 95% confidence interval was 0.028 plus or minus 0.008, and the slope was 0.025 plus or minus 0.003 relativity over milliliters. Using the standard addition curve, the concentration of riboflavin in the solution was determined with this equation. Cx is the concentration of the riboflavin, which is equal to the intercept times the concentration of the standard solution divided by the slope times the volume of the unknown riboflavin solution added. So, the concentration of the unknown riboflavin solution was 11 plus or minus 5 parts per million. The theoretical riboflavin concentration was 10 parts per million. The mass percent and percent error of the riboflavin was calculated using the same equations as the ones used for the standard solutions. The mass percent of riboflavin in the multivitamin was 6% for the experimental value and 5.1% for the theoretical value. The percent error of the mass percent of riboflavin in the multivitamin was 10%. In conclusion, for the standard solution method, the experimental mass percent of riboflavin was 6.6%. The theoretical mass percent of riboflavin was 5.1%, and the percent error was 28.6%. For the standard addition method, the experimental mass percent of riboflavin was 6%, the theoretical mass percent of riboflavin was 5.1%, and the percent error was 10%. Some possible sources of error may be caused by some of the solution flasks being inaccurately filled. Some were slightly filled above the calibration line. The experimental results showed that the standard addition method was more accurate than the standard solution method, since the mass percent of the riboflavin was closer to the theoretical in the standard addition method than in the standard solution method. This matches with the theory explained in the background, since standard addition takes into account of the interferences of the other substances in the multivitamin.